Common mode feedback. In this and previous chapters, we have described many advantages of fully differential circuits over their single-ended counterparts. In addition to greater output swings, differential op-amps avoid mirror poles, thus achieving a higher closed loop speed. However, a high gain differential circuits require common mode feedback CMFB. To understand the speed for CMFB, let us begin with a simple realization of a differential amplifier. Figure A. In some applications, we short the inputs and outputs for a part of the operation. Figure B. Providing differential negative feedback. The input and output common mode levels in this case are quite well defined, equal to VDD minus ISS RD by 2. Here you can see in this figure a simple differential pair B circuit with inputs shorted to outputs. Now suppose the load resistors are replaced by PMOS current sources so as to increase the differential voltage gain. Figure A. What is the common mode level at nodes S? Here you can see in this figure a high gain differential pair with input shorted to outputs, B effect of current mismatches, and Y. Since each of the input transistors carries a current of ISS by 2, the CM level depends on how close ID3 and ID4 are to this value. In practice, as exemplified by figure B, mismatches in the PMOS and NMOS current errors defining ISS and ID3-4 create a finite error between ID3-4 and ISS2. Suppose for example that the drain currents of M3 and M4 in the saturation region are slightly greater than ISS by 2. As a result, to satisfy Kirchhoff's current law at nodes S and Y, both M3 and M4 must enter the triode region so that their drain currents fall to ISS by 2. Conversely, if ID3-4 less than ISS by 2, then both Vs and Vy must drop so that M5 enters the triode region, thereby producing only I2ID3-4. The above difficulties fundamentally arise because in high gain amplifiers we wish a P-type current source to balance an N-type current source. As illustrated in figure, the difference between IP and IN flow through the intrinsic output impedance of the. Here you can see in this figure simplified model of high gain amplifier creating an output voltage change of IP minus IN RP parallel to RN. Since the current error depends on mismatches and RP parallel to RN is quite high, the voltage error may be large, thus driving the P-type or N-type current source into the triode region. As a general rule, if the output CM level cannot be determined by visual inspection and requires calculation based on device properties and it is poorly defined, this is the case in figure but not in figure. We emphasize that differential feedback cannot define the CM level. The foregoing study implies that in high gain amplifiers the output CM level is quite sensitive to device properties and mismatches and it cannot be stabilized by means of differential feedback. As a common mode feedback network must be added to sense the CM level of the two outputs and accordingly adjust one of the bias currents in the amplifier. Following our review Following our view of feedback systems in chapter, we divide the task of CMFB into three operations: sensing the output CM level, comparison with a reference, and returning the error to the amplifier's bias network. Figure conceptually illustrates the idea. In order to sense the CM level, we recall that Vout CM is equals to Vout1 minus plus Vout2 by 2, where Vout1 and Vout2 are single-ended outputs. It therefore seems plausible to employ a resistive divider as shown in figure. Generating Vout CM is equals to R1 Vout2 plus R2 Vout1 by R1 plus R2, which reduces to Vout1 plus Vout2 by 2 if R1 is equals to R2. The difficulty, however, is that R1 and R2 must be much greater than the output impedance of the op-amp so as to avoid lowering the open loop gain. For example, in the design of figure, the output impedance equals 266 kilo ohm. Here you can see in this figure conceptual topology for common mode feedback. Here you can see in this figure common mode feedback with resistive sensing. Necessitating a value of several megaohms of R1 and R2 as is explained in chapter. Such large resistors occupy a large area and, more importantly, suffer from substantial parasitic capacitance to the substrate. To eliminate the resistive loading, we can interpose source followers between each output and its corresponding resistance. Illustrated in figure, this technique produces a CM level that is in fact lower than the output CM level by VGS78, and this shift can be taken into account in the comparison operation. Note that R1 and R2 or I1 and I2 must be large enough to ensure that M1, M7 and M8 is not starved when large differential swings appear at the output. As conceptually depicted in figure, if say Vout2 is quite higher than Vout1, and I1 must sink both Ix similar to Vout2 minus Vout1 by R1 plus R2 and ID7. Subsequently, if R1 and R1 plus R2 or I1 is not subsequently large, ID7 drops to 0 and Vout CM no longer represents the true output CM level. His sensing method of figure nevertheless suffers from an important drawback. It limits the differential output swings even if R12 and I12 are large enough. To understand why, let us determine the minimum allowable level of Vout1 and Vout2, nothing that without CMFB it would be equal to VOD3 plus VOD5 with a source follower in place. Vout1 min is equals to VGS7 plus VI1, where VI1 denotes the minimum voltage required across I1. This is roughly equal to 2 overdrive voltages plus 1 threshold voltage. Thus, the swing at each output is reduced by approximately VTH, a significant value in low voltage design. Here you can see the figure of common mode feedback using source followers. Here you can see the figure arranged starvation of source followers for large swings. Looking at figure, the reader may wonder if the output CM level can be sensed by means of capacitors rather than resistors so as to avoid degrading the low frequency open loop gain of the op-amp. This is indeed possible in some cases and will be studied in chapter. Another type of CM sensing is depicted in figure here indicated. Here identical transistors M7 and M8 operate in deep triode region, introducing a total resistance between P and ground equal to R tot is equals to R on 7 parallel to R on 8 is equals to 1 by N nu n C naught x W by L V out 1 minus VTH parallel to 1 by nu n C naught x W by L V out 2 by minus VTH is equals to 1 by nu n C naught x W by L V out 2 plus V out 1 minus 2 VTH, where W by L denotes the aspect ratio of M7 and M8. Equation indicates that R tot is a function of V out 2 plus V out 1 but independent of V out 2 minus V out 1. From figure we observe that if the outputs rise together, then R tot drops, whereas if they change differentially, one R on increases and the other decreases. Common mode sensing using MOSFET operating in deep triode region. In the circuit of figure, the use of M7 and M8 limits the output voltage swings. Here it may seem that V out min is equals to VTH 878, which is relatively close to 2 overdrive voltages, but the difficulty arises from the assumption above that M7 and M8 operate in deep triode region. In fact, if say V out 1 drops from the equilibrium CM level to one threshold voltage above ground, and V out 2 rises by the same amount, then M7 enters the saturation region, thus exhibiting a variation in its own resistance that is not counterbalanced by that of M8. We now study techniques of comparing the measured CM level with the reference and returning the error to the op-amp's bias network. In the circuit of figure, we employ a simple amplifier to detect the difference between V out CM and a reference voltage Vref, applying the result to the NMOS current sources with negative feedback. If both V out 1 and V out 2 rise, so does VE, thereby increasing the drain currents of M3 minus M4 and lowering the output CM level. In other words, if the loop gain is large, the feedback network forces the CM level of V out 1 and V out 2 to approach Vref. Note that the feedback can be applied to the PMOS current sources as well. Also, the feedback may control only a fraction of the current to allow optimization of the settling behavior. For example, each of M3 and M4, here you can see in this figure, sensing and controlling output CM level, can be decomposed into two parallel devices, one biased at a constant current and the other driven by the error amplifier. In a folded cascade op-amp, the CM feedback may control the tail current of the input differential pair. Illustrated in figure, this method increases the tail current if V out 1 and V out 2 rise, lowering the drain currents of M5 minus M6 and storing the output CM level. Here you can see in this figure alternative method of controlling output CM level. How do we perform comparison and feedback with the sensing scheme of figure? Here the output CM voltage is directly converted to a resistance or a current, prohibiting comparison with a reference voltage. A simple feedback topology utilizing this technique is depicted in figure, where R on 7 parallel to R on 8, adjust the bias current of M5 and M6. The output CM level sets R on 7 parallel to R on 8 such that ID5 and ID6 exactly balance ID9 and ID10 respectively. Assuming ID9 is equals to ID10 is equals to ID, we must have VB is equals to VGS5 is equals to V is equal to ID R on 7 parallel to R on 8, and hence here you can see in this figure CMFB using triode devices. R on 7 parallel to R on 8 is equals to VB minus VGS5 parallel to by 2ID from equation 1 by nu and C naught x W by L 7 8 V out 2 plus V out 1 minus 2 VTH is equals to VB minus 2 minus VGS5 by 2ID, that is V out 1 plus V out 2, V out 1 minus V out 2 is equal to 2ID by nu and C naught x W by L 7 8 into 1 by VB minus VGS5 plus 2 VTH. The CM level can thus be obtained by nothing that VGS5 is equal to root over 2 ID by nu and C naught x W by L5 plus VTH5. The CMFB network of figure suffers from several drawbacks. First, the value of the output CM level is a function of device parameters. Second, the voltage drops across R0 7 parallel R0 8 limits the output voltage swings. The third, to minimize this drop, M7 and M8 are usually quite wide devices introducing substantial capacitance at the output. The second issue can be alleviated by applying the feedback to the tail current of the input differential pair figure, but the other two remain. Here you can see in this figure alternative method of controlling output CM level. How is VB generated in figure? We note that V out CM is somewhat sensitive to the value of VB if VB is higher than expected. The tail current of M1 minus M2 increases and the output CM level fails. Since the feedback through M7 and M8 attempts to correct this error, the overall change in V out CM depends on the loop gain in the CMFB network. This is studied in the following example. We now introduce a modification of the circuit of figure that both makes the output level relatively independent of device parameters and lowers the sensitivity of the value of VB, illustrated in figure A. The idea to define VB by current mirror arrangement such that ID9 tracks I1 and Iref. For simplicity, suppose W by L 15 is equal to W by L9, and here you can see the figure modification of CMFB for more accurate definition of output MC level. The W by L16 equal to W by L7 plus W by L9 as ID9 is equals to I1 only if V out CM is equal to Iref, Vref. In other words, as with figure, the circuit produces an output CM level equal to a reference, but it requires no resistors in sensing V out CM. The overall design can be simplified as shown in figure B. In practice, since VDS15 not equal to VDS9, channel length modulation results in a finite error. Figure depicts a modification that suppresses this error. Here the transistors M17 and M18. In this figure you can see modification to suppress error due to channel length modulation. Reproduce at the drain of M15 a voltage equal to the source voltage of M1 and M2, ensuring that VDS15 is equal to VDS9. To arrive at another CM feedback topology, let us consider the simple differential pair shown in figure A. Here the output CM level VDD minus VGS34 is relatively well defined, but the voltage gain is low. To increase the differential gain, the PMOS devices must operate as a current sources for differential signals. We therefore modify the circuit depicted in figure B, where for differential changes at Vout1 and Vout2, node P is a virtual ground, and gain can be expressed as GM12 R012 parallel to R034 parallel to R7. The common mode levels, on the other hand, M3 and M4, operate as diode connected devices. The circuit proves useful in low gain appliances. It is important to know that fully differential two-stage op-amps such that in figure require two CMFB networks, one for the output each stage, and an example is described in a differential pair using diode connected loads B resistive CMFB. Thank you.